All right, so I'll just start my talk. As you said today, language is a measures of smell. And, I came into this field thanks to two collaborators, one of them who has become also a very dear friend. I stole a slide from him. Um, we came together trying to solve a question, which is, how can it be that two molecules that have very different structures smell the same, right? How is it possible uh, that both smell like almonds? So that was one of the first questions that we wanted to solve. And as you know, Andreas and Leslie Voskhol got together a very large data set, public data set, that I'll talk about a little bit later. But I came into this precisely as just, an organizer of crowdsourcing competition, which is called Dream. And I really thought this was, an amazing problem to try to solve. Can we really predict what a molecule smells like just from structures? The second question, which I think is really interesting, is how we describe the odor of a molecule, right? And the only way to describe is semantically. So this is also a slide I stole from Leslie Voskhol. And you'll see here, of course, odors are mainly mixtures of odors. And if you see all these different molecules, you can assign, a word if you want, or a descriptor to what they smell like. And some people would say, well, this is not super precise, etc. But there's even a question that's even more complicated than this, right? Which is, how does the mix of all these molecules, with all these different descriptors, can give you the smell of something that seems in a way very different? And you might have seen this slide before. You might know what I'm talking about. So basically, the smell of the aroma of all these different molecules is actually the aroma of coffee. And in a sense, the big question is, how do you go from this ensemble of descriptors to something that is defined as smelling like coffee? And it's true that if you go through all these different descriptors and think about coffee, they are there somewhere hidden in the aroma of coffee, right? But how does this really happen? I think we don't know, and we don't have an answer yet. And I guess one of the reasons also underlying this has been this, underlying idea that language is just not good at describing smells, right? And I think that the first thing is because, well, I mean, yeah, we're bad at actually recognizing smells, right? When we, so for example, this image, right? I mean, you're not even smelling it, but maybe you thought this was coffee, right? But it's actually chocolate. I was trying to, induce you into a mistake from this image to this image, and maybe, it's the afternoon in Europe, but here in the US, I just got my coffee, and so when I see this image, I really think of coffee, right? And of course, I would be able to distinguish the aroma of coffee from chocolate. They're very different. But it's true that without a context, just humans in general, we're bad at assigning a descriptor to a smell. This is something that's known. And so there's this idea that, really language is just, not very good at describing smells. And, only people like Christophe Lodamiel or, specialists could really use a huge amount of descriptors for smell. But I think one of the interesting ideas really that shocked me when I got into the field of olfaction is the fact that the olfactory bulb directly projects to the cortex, and the whole timing, and instead of going through the hypothalamus, right? This is the only sensorial one of our senses that go directly to the olfactory cortex, and in a sense, that the whole timing of this is also pretty much associated with the speed with which we speak. So I think one of the problems with the ideas behind why language, and of course now I'm talking about what Asif Majid would call the Occidental language, right? So the Occidental Western civilization, where language is not adapted because we know that other civilizations that she has studied or other ethnic groups do have specific words for smell, right? In our case, it seems that smell is always associated with an object, and there don't seem to be classes of descriptors that go beyond an assignation of an object, right? So, for example, there's this famous data set, the graphics data set, where 500 experts chose and selected a set of descriptors, which are described here. And those are, most of them are associated to, a fruit or an object or something like that. And the claim is that, the difference between smell and, for example, vision is that, there's not such classes, or if you want, object-free descriptors for smell. So in vision, you have, red, green, blue, and then, violet, and you have different words that really describe the color. I would actually claim that this is true for vision, right? It is more, there's more, if you want, classes and of colors. But it's true also that if you go beyond, these general classes of odors, and you start describing more complex colors, then you start having to put an adjective on them, right? Like deep blue or rosa mexicano, or you rapidly lose definitions, and you need to refer to objects or to countries or things like that. So I do think it's true that vision has more classes, but rapidly we fall into the same problem as olfaction. And of course, the driving data set, and I think the driving data set was actually it's a great resource. But one of the problems it had was that it was just too sparse, right? There were too many words, and not enough molecules in a sense. And so that's why I think Leslie and Andreas decided to create a new data set, which is known now as kind of the dream data set, that used a larger amount of molecules. Some of the molecules overlap with Drafniak's, but also used some of the words, right? Not the 140 or so words that we're using in Drafniak's, but something more simple. Just use 19 words and intensity and pleasantness. And really, I think that this was, there were a couple of reasons for why I think this was genius to select this. And when we're trying to define the challenge, we said, well, we know that words are just difficult to predict, right? From Drafniak's. Nobody has really been able to predict drivings from the structures of molecules. So, let's concentrate on intensity and pleasantness, and, let's try to see if they can predict some of these words. So the idea of the descriptors was really, let's do this as an experiment, but really we want to try to predict intensity and pleasantness. So this is what we did. We organized a Dream Olfaction Challenge. We, separated the 400 molecules into a large training set of 300 molecules, and then a leaderboard set to enhance competition, and then a hidden set. And we gave the participants these, a set of molecular features. We were, in this case, the dragon descriptors, but they really could, use any representation of molecules to predict. The idea was to try to predict, what the hidden set of molecules were going to smell like. And so what was interesting is that, the best performing model from Yang-Fan Guan and also Rick Gherkin used random forests, right? So basically a nonlinear model that would associate different groups to specific descriptors. But what was also interesting is that, a second place model was actually just a linear model that was using a linear regression with lasso regularization. So in a sense, we could say that every descriptor of the molecule was contributing independently to the prediction. And that a little bit, in what was, it was not the best model, but it was really high. And what was interesting about this is basically, if you have a linear model where each of the different, if you want, descriptors of the molecule is contributing independently, it really means that, you can explain why two molecules that have a very different structure could still bring the same smell. In this case, the smell of almond is because, different parts contribute independently. And so they don't need to be exactly the same. They just need to share some of the descriptors that, bring the almondy sensation, if you want. So these are the results of the challenge. You probably have seen them, but you know, this is how, again, as I said, we did it. We were scoring. There were like, you know, about 20 teams that participated, and we were scoring the correlation between their predictions and the values of intensity across molecules and pleasantness. And you can see intensity and pleasantness are pretty high. And then in green, you see this is basically the average across the different descriptors, right? And the prediction is not as good, but it's pretty large, right? And you can see here, just to show that the predictions were actually good, right? If you plot the actual measure versus the prediction, the correlation is pretty large. And actually, one thing is, this is of course predicting the means across the 49 subjects, because as you know, the individual ratings are really hard to predict. So it is true that there's a high diversity of ratings between people, but if you take the average, if you want the population, then you know it becomes much more stable. And so I think really the big surprise of the challenge, beyond the fact that we could really predict well intensity and pleasantness, was that we could predict well, you know, a lot of these descriptors. So garlic, fish, sweet, fruit, burnt, all these, you know, had a correlation of above 0.5. And I think this was really a big surprise, because not until now, I think the properties that people were only trying to predict were intensity and pleasantness. So really this idea that we humans are not good at even generating, you know, probably stable data that can be used for predictions when we use descriptors, we could only predict, you know, whether it's intense or not, and pleasant, right? And whether maybe that's associated with, you know, how your grandmother cooked, or, you know, smells that you had in infancy, right? So nothing that could be put in terms of specific descriptors. So this was kind of a big surprise from the challenge, to me at least, and I think also to Leslie and Andreas. And one of the things I I want to point out, and this was a great idea to analyze from Joel Mainline, who also participated, you know, his group participated as a they submitted a model, but was, you know, again, this data set is great, and for 20 of the molecules, they basically repeated the ratings to see the stability of the ratings across the test and retest. And basically, what you see here is the test-retest correlation. Basically, how correlated are two measures for across these 20 molecules for each of the descriptors, and how good the model is, right? At also predicting one or the other. And what you see is basically that for some descriptors, such as, you know, warm, grass, urinous, cold, so the first 5, right, the test-retest is pretty bad. So actually, people are not very good at using these descriptors. And the model is also, of course, not very good at predicting, because if, you know, you don't have very stable data, your model is not going to be good. But then there are some predictors which are on the top right, such as sweet, garlic, fruit, and fish, which are pretty stable across, you know, doing a test-retest correlation, and also the model is pretty good, right? So of course, we're not good at using all of these descriptors, but there are definitely some that are pretty stable, right? And so basically now, you know, since this paper, you know, we can, if you have a desired profile, you can select a set of, you know, molecular structures and actually try to predict, you know, try to find the best molecule to have the desired profile that you want, right? So you can basically match a list of molecules to what they actually smell like. And so, you know, this is the first time that it was tried, and it was possible thanks to, again, the fact that these descriptors were a smaller set than the Draftniks. I think that was really the important part in order to be able to meet models. But then what right away came to us was, well, I mean, can we actually try to predict the Draftniks? I mean, we know, and we tried that directly, it's not possible. Just the data is too sparse. So now that we have a good model to predict some of these descriptors, can we actually use the model to predict, you know, with these pure molecules, even more descriptors? And so what we decided to do was, again, take this idea that actually, you know, you could use the properties of language and the properties of natural language processing. And so the idea is, well, we have now this cheminformatic model where from any molecule we can predict the dream descriptors. But what about if we use some of these, you know, word representations that have exploded in the past few years, where we can use some of the neural networks, the representation of words by neural networks, to implement a better model where we could predict more descriptors. And how should we do that? Well, I mean, how this is done? For example, this fast text basically tries to predict which word is going to come after a word, and what is the frequency and what is the probability of the word to come after another. So if we concentrate on things that have words that describe others, then the properties of these words could also reflect the structure, if you want, of the olfactory space. So the idea is that the olfactory space and how we rate things with descriptors is actually not unsimilar to the linguistic space. And so, for example, if two vectors are close in the olfactory space, such as flower and fruit, they will also be close in the vector representation of words in language. And so the idea would be we would use this projection to then predict the driving descriptors. And so what you see here is actually the set of driving descriptors that we try to predict, represented based on their semantic distance. And the semantic distance is basically just this angle between two vectors in the space of vectors in the neural network. And in blue, you have basically all the words. And in red, you have the words that were selected, the descriptors were selected for the dream challenge. And you see that this is another a great, idea of, and this just came, I think, naturally when I always ask Andreas or Leslie, like, how did you choose the descriptors? They were, well, they just made sense, and we wanted to choose a subselection of the Drafniaks. So what you see here is that the descriptors that are selected in red actually really go around, if you want, the semantic space, right? They're not clustered on one side. They really cover all of it. And it's also interesting to see that, there's some antonyms that are really close, right? Like warm and cold. I mean, they're close semantically because they're very often used in similar contexts, right? But of course, it doesn't mean that two things are going to smell exactly the same. So of course, the linguistic models have sometimes some problems. And in general, it makes sense. If you look, like fruits are clustered together, alcoholic smells and more kind of like animal smells are clustered together. Flowers, etc. So really the semantic, if you want, classification of these kind of makes sense also in the olfactory space. So then we use this, if you want, hidden layer that represents a vector in the neural network. So it's what we call now embeddings, to really build a model where, if you want, the closer two words are in the vectorial space of language, the closer they will be in the olfactory space. And that's basically the simple idea behind what we did. And when we do that, we now get here the predictions that our model had. So in red, you have high correlations, and we have some anti-correlations also in blue. But you see that overall, we got a pretty good prediction for the driving descriptors. And we can use a model that doesn't use the ratings at all, that just use the semantic, and we have some correlations that are bad. But now if we use the ratings for the sets of molecules that overlap between dream and Drafniaks, then we get a much better correlation, and we start to having, for up to about 60 of the descriptors, a correlation higher than 0.4. So a very good description. So in a sense, really the conclusion to me of this paper and was that you can discuss whether descriptors are good or are not good for describing a smell, and how stable they are, and whether Western language is adapted or not. But the fact that you can use linguistic tools to build models that predict things, and to me is maybe it's not an intellectual proof, but it's a practical proof that you can take advantage of language in the context of smell descriptions and do practical things with them. And so the second part of my talk is really about what some ideas that we've developed on what can you do with now these tools, if you want, linguistics tools that you can implement as models. So one of the things we also did in that paper was just to show that we could go beyond the Drafniaks. I think we took the families of molecules such as acid, ketones, alcohol, and aldehydes. We collected all the words that were used to describe these families, and we extract these from good scents. So all these cocoa, balsam, banana, whiskey. And then what we did is, for each of the different words, we took the top 10 predictions from our linguistic model and looked at how well this correlated with the actual values, right? So in left here, in blue, you have the actual top 10 descriptors for pentanoic acid, right? And for example, our model predicted that pentanoic acid indeed smells like sour, sweety, rancid, and acid, right? From the top 10, we got 4 correctly. And same with eptanon and same with hexanon. So basically, we now could, if you want, predict words from descriptors from molecules that we had never seen by just, taking, if you want, the universe of words that describe these families. And here you see the summary for each of these molecules, and you see different families are predicted in different way, but the AUC of the prediction is pretty good. Aldehydes seem to be harder to predict. So each of these points represents one of the molecules that you see here on the left, and then you have the overall, if you want, statistics, right? So this shows that, again, we can use this, if you want, dream model on top with followed by a linguistic model to try to predict any descriptor, right? Here we go beyond the ones we saw in DraftNext, and we can still get a pretty good prediction. So now I move to something else that has to do now with how can we really implement these as a measure of smell, in a sense, right? And when you think about this measure of smell, for example, you know that we're very good at discriminating odors. Mixtures of odors, right? So now we go to mixtures of odors, and you probably know all these discrimination text experiment. I think it's pretty cool. Basically the idea is you have 3 vials. In 2 vials you have the same mixture. In the third one you have a different one, and the subjects have to distinguish which one is different. And sometimes some of the tricks that you do is the 2 mixtures are the same. You put just a different dilution so that they are. It's not about. It's really about the other having a different nature, if you want. And the idea is, well, can we use a language as a ruler in the sense of, the measurement is what is the percentage of people that can really distinguish these 2 mixtures, and can you predict that? Can you predict how well people will distinguish 2 mixtures? And so so if you have a mixture A and a mixture B, it has a set of molecules, and of course this is all for now equi-intense, except for one case that I will show. And so can you actually find the metric, meaning what is the distance between these 2 mixtures as measured by the percentage of subjects that can distinguish them? And this is actually something that was done before, tried before by the Sobel group, by Snitz. And the idea was, what they did is they said, well, a mixture is just a set of molecules, and these molecules have descriptors. So let's just, aggregate all of these descriptors into a single vector and then measure an angle between the vectors. And let's select the top descriptors that give you an angle that correlates with the metric, right? And this is what they did, and they had relatively good results. But what we decided to do is, well, can we take advantage now of, our trained model on descriptors to try to bring more information than just, select the top descriptors. And so what we do in our case is, we implement the model, and for each of these mixtures, and I'll tell you how we do it, we try to predict what they smell like, these mixtures smell like, in the space of the 19 descriptors of dream, of actually 21 with pleasantness and intensity. And then we try to find the metric between these 2 descriptions, right? So instead of the space of descriptors, we're now in the space of molecular descriptors, we're in the space of linguistic descriptors. So this is the setup. So what we do is, for each of these molecules with our model, we can predict what they smell like in this the descriptor, linguistic descriptor space. Then what we do is we just take the average, or we can also take the maximum, which is a second option. And this would be, basically, it's just a linear integration of what each of the molecule contributes, given that they're equi-intense. And we know this is not a good approximation. We know precisely that, as I was describing with coffee, the addition of all the descriptors of the molecules that compose something doesn't give you, rarely gives you the overall sensation. So there are non-linearities, and this is known, right? So how do we take care of the non-linearities? Well, what we do is, instead of trying to fit, if you want, an Euclidean distance between, these 21 descriptors, so just what you calculate for each descriptor distance, you try to do what we call in machine learning metric learning. So for each of the components, you add a variable that you assign, that you can vary, right, when you're calculating the Euclidean distance. And I'll show you in a second the equation. And then, you can fit a metric that, in a sense, will take care of the nonlinearities. And so for that, we used, of course, the Bush-Dit data set, which is perfectly designed for this, because it measures the distance between mixtures when you change the overlap. And so that, in a sense, you're building a metric by separating more and more the mixtures. And so when we do that, for example, and we do this setup to get the metric learning, we obtain a much better result than just using an Euclidean distance, in a sense. And so this is just the setup that we did in order to be able to predict just using Bush-Dit. And what was great is that, there are some external data sets that used by SNITs, and two types of data sets. And also recently, the Ravia data set that was published in Nature, where they claimed that they found some metamers. And what you can see in white is our predictions, and we used the root mean square error. And so basically our model, the semantic model, if you want, does much better than the direct model, which is this angle model that was implemented by the Sobel lab. And actually, it does much better with data that it has not ever seen, right? We just used the Bush-Dit data set to predict. The correlation is actually comparable between the models, but I really think that root mean square error in this case is a better measure. And also, in the case of the SNITS data, for example, SNITS 2, in some cases the mixtures have 2 molecules, in some cases they have 30 molecules. So it seems to be agnostic to actually the number of molecules that are in the mixtures. And of course, in Bush-Dit, most of the molecules had 10, 20, or 30 mixtures. So what can we do with this model besides just predicting correctly, more or less correctly, the distances between mixtures? Well, we can, for once, for example, predict the average distance between mixtures in data sets. And as you can see in Bush-Dit, Ravia, and SNITS, we do pretty well. And actually, we can use this to show that the DREAM data set, that of course is not a mixture, it's just single molecule, but as I said, it works also for single molecules, has a much larger distance between the molecules than the average mixture data set. And that makes sense because DREAM really, DREAM data set was trying to get a universe of smells. So when we analyze the model, the other interesting thing about it is that when we did the metric learning, actually for 10 of the 21 descriptors, the coefficient was 0. So basically, they didn't contribute to the distance between mixtures. The only descriptors that contributed were the ones here in blue. So fish, burnt, cold, garlic, sour, sweet, bakery, intensity, grass, and chemical. And what's interesting is that, again, if you go back to this dendrogram of distance between descriptors in the semantic space, you see in blue are the ones that we kept, and in green are the ones that, the color ones are all DREAM descriptors, but the ones in blue are the ones that were kept by the model to calculate the metric learning. And in red were the ones that were taken out. And as you can see, they seem to be paired in most of the cases, right? So they got rid of the descriptor that was basically just not contributing any information, and they're very close in the semantic space. So again, I think this is one more addition to show that really a semantic space is a good space for trying to interpret, what is going on in the perceptual space, in the olfaction perceptual space, right? You're getting rid of the descriptors that are very close in the semantic space and then are not bringing any information in the olfactory space for trying to predict similarities. Okay, so just to end up this part, I mean, one of the things that you can do now that you have a model, you can just predict distances between, you know, any set of mixtures. And so what we do here is we just took 100 molecules and try to predict distances between mixtures by changing the percentage overlap. And so we start, if you want, getting a shape of what the space looks like. So again, you know, the more mixtures you have, it seems that you're, you know, you get into this olfactory white noise where everything starts smelling similarly. But you know, the less overlap there is, the farther away the mixtures are. And of course, the more molecules you have, the closer they will seem alike. Now, also, if you add up more mixtures, more molecules in the mixtures from 0 to 100, the distance between the mixtures will also kind of go down. This is just basic an effect of the averaging that we're doing, right? So now, if you put this in the 3-dimension space where you have, you know, the metrics, so basically the distance between molecules compared to the number of molecules in the mixtures and the overlap, you see that if you want the space of things that can be differentiated is actually, you know, not as wide as you would think. And so the last thing we did is here you have a plot of the learned metric basically versus the actual measured metric. And what you see here is you have this zone that's shown by this heat plot, right? Where a lot of the molecules are, and where if you change a little bit the metric, your distance between the mixtures changes a lot, right? So it's kind of like a very unstable region where if you change a little bit the distance, then the perception will go from not being distinguishable to being totally distinguishable. So this, in my view, can be interpreted using these you know, perception curves, where in green you have, and again, this is the plot of a metric versus the actual measure. And so you can interpret why metamers are so difficult to find. And the idea here is that, you know, if you want a metamer, then you have to be in a region where if you change a little bit the metric, the actual value of the distance between the mixtures doesn't change a lot, right? So for example, the green curve, you can have metamers because you have a long tail, right? And so you can there have things where you change the metric, but things are still indistinguishable. You can also have metamers in the green, in the red curve, and in this case, even if it doesn't have a tail, still, right, because the curve is not very steep, you can change a little bit the metric, so the distance between the two mixtures, and you can still find things that will smell very similarly. The problem is, I think that we are in the situation which is the blue situation, that's depicted by the data on the left, where, you know, if you change a little bit the metric, so first of all, there's no tail, right? There's no flat tail. And if you change a little bit the metric, the curve is pretty steep, and you will rapidly go from you know, not being to distinguish to actually being able to distinguish the two mixtures. So that's why, I mean, I think that metamers exist, and Sobel showed this, but I think they're very, very hard to find, right? And metamers, again, being mixtures that have no molecules in common, but that smell the same. So these, I think, are very hard to find. I think our results from our model kind of show a little bit that. Okay, so now the last, so I think really this shows that you can use, you know, implement language in a model to have a better prediction of distances, right? So as if language was really bringing, and of course, the fact that we collected this large stream data set is really bringing an extra information to being able to measure the distance between mixtures. Now, the last thing that I think language can be used for is as a diagnostic tool. And, you know, we were very unlucky to fall into this, you know, COVID quagmire for the past 3 years. But one of the things I would think was very interesting is, you know, this global consortium on chemosensory research that formed very rapidly in this amazing community that is the olfactory and the chemosensory community, right? I mean, I think this is really amazing to still see science groups that are small enough that they can rapidly coordinate and if you want, build up a community and actually generate a lot of information about a new disease. And so in this case, as fast as April 2020, the GCCR consortium, and I'll name a few of the participants, generated this survey and telecasted it, right? We're asking whether people had COVID or not, and there were several options here, but basically some were diagnosed with symptoms or with viral with another lab test, and then some people had a negative test but symptoms, and some people didn't have any symptoms. And of course, around that time, everyone was saying, well, loss of smell for COVID, etc., and that's why we, and loss of taste and loss of chemesthesis, although people really don't know what chemesthesis is, but if you tell them vinegar, then that worked. That's a good illustration. And so they sent out this survey to try to really kind of pan out whether what was going on with smell. And indeed, a lot of the people replied because they were seeing changes in their perception with smell and taste. And one of the things that we added, and I was lucky enough to be part of that group, was, well, why don't we add them, apart from a ratings question of how much their smell or taste has gone down with their disease, can we actually ask them to describe what changed, right? And so we had 4 questions where we asked them to describe any changes in smell or any changes in taste during the illness or other sensations. And then we had a very specific one, which is think about a food or beverage you consume regularly, for example, morning coffee or tea, or a piece of fruit you have each day, and how taste, smell, or flavor have changed during your respiratory illnesses, right? And amazingly, we had a lot of responses in different languages. I'm just going to concentrate now on some of the results that we recently got with Hongyang Li in my group. And the idea was, it had been shown that, of course, smell, taste, and chemesthesis change due to at least the first wave of COVID, right? With Omicron, I think things are a bit different. It has also been shown in a paper, led by Rick Gerkin, that change of ratings, although, people that didn't have COVID also felt some changes in smell, they were much more abrupt for COVID, and it was possible to actually build a model, a logistic regression model that would tell you, who has COVID and who doesn't, basically based on these perceptions more than other symptoms. So we took this further and we said, well, can we actually try to analyze the responses to these questions to try to predict who has COVID and who doesn't, and for example, who has symptoms, and who also people that don't have symptoms, right? And so we did that. We collected, if you want, the data from the questionnaire, and people would say, and I'll give you a few examples, right? Things like, I lost smell, I can test food, whether food is sweet or sour, I cannot smell anything. So there were several examples. And so the idea is we're trying to build a model, one of these large language models, to try to predict whether you have COVID or not. And then analyze the features, right? Which is interesting, like which words are more predictive of one or another. So we use this distilled bird model from Hugging Face. And actually, just an anecdote, Due Viela is the head of science research in Hugging Face, and actually he was one of the first ones that built up a model that tried to predict olfaction based on again, words. So he probably will be happy to see this work, where now we use a much more advanced model, right? So basically the idea is you can take any sentence or paragraph, tokenize it, and then use it in a transformer, in an encoder. We already have a pre-trained model. We just need to adapt it to this specific data set if you want. So we have already a large language model. And when we do that, we get the following results. So what we try to predict is people that have COVID, as designed by a viral test, distinguished from people that either don't have COVID but have symptoms, and this is option 5, or don't have COVID and don't have any symptoms, right? And so what you see in red is for the people that have symptoms. We are able to distinguish. The AUC is a little bit above 6.6, 618, and we don't do as good as the ratings model, which is 0.72. You see the white dot, but we're still able to distinguish based on that. And then, of course, option 6, where people have no symptoms and have no COVID, is easier to predict than people that have symptoms but that don't have COVID, right? So the model seems to work. And so now what's interesting is you can look at the feature interpretation, and this is the frequency of words that people use to describe their sensation. As you see, a lot of things are smell, taste. So the bigger the word, the most frequently it is used. And now we can also extract the features of the model, which are the words that actually the model uses. And as you can see, there's a change, right? It's not because the word is more frequent that you're going to use it more. So for example, here's taste is much smaller, or smell is much smaller. But now you start seeing things that are a bit larger, that are more interesting, right? Like salty, spicy, sour, sweet, mint. Things that you can really associate with maybe what's really the virus doing in terms of how you're perceiving these things. Of course, the other thing that appears a lot is this, what we call these sentiment type words, right? Which are things that are just based on values, like, I can or I cannot, I completely or anything. So these are really words that bring, if you want a sentiment value to whatever you're describing. And these are also important. So now what's cool about this model is that we can really kind of take a sentence from, this is a patient that was predicted as having COVID in a very clear way. And so he says, I can't smell at all. I can't taste if the food is sweet, sour, bitter, salty, but that's all no flavored when I brush my teeth. I can't taste the mint or the mouthwash at all. Carbonated drinks can't feel the tingling at all. And you can see, with the bars, like how important were each of these words for being sure that the person has COVID. In this case, what was interesting was, carbonated drinks, that basically chemostasis, right? And all this part of the sentence on the top where you say, I can taste the food, but sweet, sour, bitter, and salty, these are some of the terms that seem important in this context, right? And this is just another example of also a pretty high, a patient that was with a high confidence predicted to have COVID, and so it says, I can't taste anything. However, I can slightly taste salt on food like crackers, right? So again, this part of what he's saying seems to be important to distinguish, between people that have symptoms and people that have COVID. And this is just a negative example. So somebody that, doesn't have COVID, of course, he just says, I haven't noticed anything special while I've had this nagging cold. So, this, and again, in this case, another example here, hot, but not until minutes later seems to be, making this patient as a negative COVID. It seems that this hot sensation not to be so associated. Anyway, so I just wanted to give you these few examples that we can really now extract information, what people are saying. People say a lot of things, which is also great. People are very verbal. And I think, in the future, these things can be used, these types of models could be used for diagnosing mental disease in neurodegenerative and neuropsychiatric diseases, such as schizophrenia or Alzheimer or Parkinson. I think we need to generate more data on that related to olfaction. And we also need more data for trying to predict other properties of mixtures of odors, such as trying to understand something I think we still don't understand, which is how all this set of molecules actually smell like coffee. So with that, I just like to thank all the people that have worked in this, from the DREAM Challenge to now the GCCR consortium. It's been a teamwork and great to be part of this community. So thanks a lot.